Okay, so I'm going to start recording now. So the first week here, we're going to cover reactions, and then we're going to jump to chapter 24, which deals with coordination compounds. And so different type of compound, we need to learn how to name these. And so we're just going to do 24.1 through 24.3, a little bit about the structure, and then mostly focus on recognizing and naming coordination compounds. After that, then we're going to come back to chapter 13, which wasn't covered in 1A. Normally people jump from 12 to 14. So we're going to come back, cover chapter 13, and then skip 14, as I was covered in 1A, and then go to 15. So 13 is thermodynamics part 2. So we're going to be looking at things like driving force in that chapter. Then when we get to 15, we're going to start something with equilibrium. And we're going to actually do a lot of equilibrium calculations. So chapter 15, 16, 17, and 18 are all equilibrium. And they all kind of have the same basic calculation. Just looking at different things regarding equilibrium. So that's going to take us more than halfway through the semester, through chapter 18. And then chapter 19 deals with electrochemistry. Chapter 20, chemical kinetics. Then we'll come back to chapter 24 and finish the remainder of the chapter, which is transition metal complexes, and then finish off the semester with chapter 25, which is nuclear chemistry. All right, at the end, the final exam is going to be comprehensive, so we're going to have the comprehensive final spread over 2 days. The first day is just going to be multiple choice, MC, and the second day will be some free response. This 13th will be 3 hours, and on the 14th it's an hour and a half or so. Let me pull this down. I was going to write some stuff on the board, but so there's going to be a bunch of other stuff that's in here but not shown. One are the midterms. Like, for example, one's the first midterm. And so if you look at the syllabus, it's not there. It's not there because for this semester I'm going to do something a bit different. That is, I'm going to do like topic exams or chapter tests. And so, for example, if we cover reactions and chapter 24, then we'll have a test like a week after. And it's going to be a very short test, one page test thing on that. And then we'll go through chapter 13. We'll do the same thing. After we finish chapter 13, then the week after, we'll have a test on that. So it's like kind of like a quiz for each chapter. But we'll have very, very short quizzes too, and I'll sprinkle those in. So let's take a look at all the stuff that's not there. That would be in this course info sheet here. So let's take a look at this. Include the audio. All right, here's my phone, and you can call me, leave a voicemail, or you can email me. Two ways. Mastering Chem is the book's website, and there are some resources there that you can take advantage of. Here. I give the catalog course description plus the course objective here. We'll read through those. Some student learning outcomes. These are mandatory from the state. Those are pretty simple. There are a lot more learning outcomes than that.
But if we were to list them in that way, it'd be too many to list.
So a prerequisite, I assume did everybody take Chem 1A here? Pretty much? No? Where did you take it?
I took it at Oregon.
Oregon? Okay. The thing you have to be careful is when you take a course mid-sequence, which I did for math, I've done that. Some chapters are repeats, some chapters are new, so sometimes it doesn't quite sync up depending on the book. Like at UCLA, it's flipped. Like they do the 1B stuff first and then the 1A stuff after that. So it's different. Anyway, getting back to this, the text, Petrucci is the same book. So fortunately you don't have to purchase that. I went to the bookstore, they don't have this available, so ignore number 2. This was the lab manual, but what I'll do is I'll just post the lab on Canvas, most likely. You will need a composition notebook, so let's take a look at one here. Now, you don't have to get one this big. This is 8.5 by 11. They sell smaller ones like the standard comp notebooks. This is nice. It has graph paper in here, which is nice to have, but if they don't have that, you can just get the college ruled one. This is where we're going to keep our lab notes. You can see here this person did that. So what this person did was they wrote the procedure over here in blue ink, and then they wrote the observations over here in black ink. That works out pretty nicely. This speeds up the lab for sure if you have everything pre-planned like this. So this is an example of that. It has to have a sewn binding, like a permanent binding. This is not a sewn, this is a glued binding, but it's fine. What you don't want are the ones that are perforated that you can tear out the sheets of graph paper and use those. Those are not accepted. Safety goggles, the same ones from Chem 1A are fine. We actually have some used pair, so if you want, you can take a pair. Scientific calculator. The scientific calculator, the one that's most useful for Chem 1B is one that does a quadratic, that has a quadratic equation solver. So if you have that, but it can't be programmable because the department has a policy against programmable calculators. So if you can just find, it used to be about $15. You know, the cheap one was $10 or under $10, and then it's the next level up. The next level up has equation solvers, and it makes it. Then most of them have, they can solve like cubic equations, third order, like AX cubed, which is useful too because once in a while we'll run into cubic equations. It'd be nice to be able to solve those using our calculator. Or if you don't have one of these, then quadratic. You want to get good and quick at the quadratic equation, which is a bit of a pain. A Sharpie. I have some Sharpies here usually, so it's nice to have your own, but if you don't, it's not a big deal. So this is optional. Recommended lab coat. I was looking for my lab coat last semester. I didn't realize I left it here. My lab coat. At UCLA, when I was a student there, they required a cotton lab coat, a heavy cotton lab coat. At the time, it was $70. Now they're like over $100. Sometimes, I think you probably can find one on Amazon under $70. But the one I bought was pretty expensive, $140 or so now. This is just a $15 lab coat. $15 lab coat's fine. All you want is you want to protect your clothes from splashes. Because normally what happens is you'll throw your clothes in the washing machine, then you get it out and there are a whole bunch of holes in it. You know, the holes came from the acid or spills or stains or whatever. So it's nice to have a lab coat. Sure. These are required now at UCLA. Nitrile gloves are also required. Nitrile is much better for most things than latex. Latex gloves aren't as chemically resistant as nitrile. But there are some chemicals that just go right through nitrile like it didn't even exist. So you have to watch out for certain chemicals. In fact, there was one, this is a pretty famous story. There's this professor, I forgot at which school, but this is fairly recent. She was wearing, I think, 2 pairs of gloves and spilled 1 drop of this methyl mercury compound on her. And then, quickly took off the gloves, washed the hands, normal hygiene stuff, wash our hands all the time. But she ended up falling ill, and then about a week later actually died from poisoning. And so even gloves, you have to be careful about the gloves. Usually we change out the gloves. If you're working in the lab all day, you usually use multiple pairs of gloves because eventually they'll absorb some chemicals, and once that happens, then it provides a pretty permeable rather than impermeable barrier. Nitriles are also more comfortable, oddly enough. These breathe a lot better than latex gloves. But you can pick those up anywhere, supermarket, wherever. Can you guys see this, or is this too small? Can you see it, Rohan? Okay. Required assignments here. Basically everything's required, especially lab and lab attendance. There's laboratory absence. This is departmental policy here. The reason it's a departmental policy is because we have an articulation agreement with the UCs and the Cal States. So at UC, the lab class is a separate class than the lecture class. Here it's combined. In order to combine the 2 classes, we have to have the stipulation that if you don't pass lab, you can't pass the class. That's so that you get both lecture and lab credit. And so the lab is worth about 23% of your grade. And you might think, okay, you can skip lab and still do okay in the class. But it's not going to work, because if you don't get at least 65% of these 230 points, you aren't going to pass. I have to fail you, and that's because of our articulation agreement here. So just be aware of that. The labs are important. If you do miss lab, you try to make it up is the best option there. We have 2 sections. We have an afternoon section and morning section. So if you can come in the afternoon section, then probably can make it up, like an extra day or something. Some labs, though, we can't because of the equipment. All right, so lab's about 23%. I have a tentative total of 1,030 points, and this could change at any time. But this is what I have so far. The final exam, which I talked about, is going to be about 20% of your grade, 200 points, broken up into 2 parts. And then we're going to have these exams, these individual chapter exams. We're going to have 9 of them, and those are going to be worth 50 points each. We're going to have some quizzes sprinkled through the semester. Those are going to be 5 points each, about 10 quizzes. Short quizzes, like 5, 10-minute, 15-minute quiz. And then homework, which is going to be worth 100 points. It's 10 points. There are 11 homework assignments. I'll just take the best 10. Okay, then the labs. The labs are 10 points per experiment for most of them, except a few of them will be worth more. For example, qualitative analysis, that's what QUAL stands for. That's going to be worth twice as much. It's going to be worth twice as much because this is a long lab. We're going to do that over, I think, 4 or 5 lab periods. Then we're going to have a synthesis lab. That's going to be worth 50 points. It's going to be worth 50 points because this lab's just going to be a 2, maybe 3 period lab. But we're going to write a report for that, a more formal scientific report for the synthesis. Also, the same thing with the titration. We're going to write a more formal scientific report for that. And then the kinetics is a little bit of extra work there. And so I'm thinking 2 formal reports, which would be the synthesis and the titration. The others are kind of fill-in-the-blank reports. This is going to be the grade distribution. This could change as well. I curve it a little bit. So 90 right now is the cutoff, but it may change, that is. I don't curve the test, I'll just curve the distribution here. Okay, note on academic honesty. Of course, is required. If you have any special requirements, let me know. And if there are changes, I'll try to let you know in lecture. And then I have this definition of chemistry here. So we take a look at this is from the American Heritage Dictionary. Well, one, the science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems. So this wasn't really written by a chemist here, because I think a chemist would have defined it maybe a little differently. And that is, they probably would have just said, the science of the composition, structure, and properties. Because reactions are just another set of properties here, and so it's not really necessary to highlight that. Because normally when we think of properties of substances, we have like two types of properties. What are those two types of properties? Yeah, Colin? Yeah, physical and chemical. Most people have no problem with physical properties. But chemical properties are more complicated, or can be more complicated. And so give me some examples of physical properties. Color and state, like solid, liquid, gas. So we can tell, can you tell me some physical properties of HCl? What color is HCl? Colorless. And do you know the state of pure HCl? It's a gas. It's a gas. Why do you want to know that? Well, one of the reasons why you want to know that is, let's say you had a bottle of 6 molar HCl and somebody left the lid off. Let's say somebody left the lid off for a week. Do you expect it to be 6 molar a week later? No, what's going to happen? What's going to happen is all the HCl is going to evaporate off the surface. That is, it's going to degas, and so by the time it's going to go flat. It's like if you have a sparkling water and you left the cap off for a week, is it still going to be sparkling? No. And so these types of things we'd like to know in case stuff like that happens. Would that be a physical change or a chemical change? So let's say it went from 6 molar down to 3 molar. Would that be a physical change or a chemical change? That would be a physical change, is the concentration. It's still HCl, Now you just have HCl in the water, that is liquid phase, but you also have HCl in the gas as well. Other things would be HCl's got to have a very low boiling point. I mean, it's a gas at room temperature. But other physical properties is it's very soluble in water. Why is it very soluble in water? Extremely soluble in water. Yeah, it's a strong acid, and strong acids typically are going to be quite, regarding structure. Structurally, it's quite, And so we come up with a kind of a general summary of solubility, and that would be, for molecular compounds like this, it would be like dissolves like. Have you heard that rule? Like dissolves like means, if you want to dissolve in water, it's got to be like water. And so in what ways is HCl like water? It's polar. It's quite polar. And so that polarity makes it pretty soluble. Does HCl hydrogen bond with water in the normal sense of hydrogen bonding? This is a bit of a trick question because Mitchell mentioned that it is a strong acid. And so we don't expect the molecules to exist in water. But if the molecules did exist in water, would they hydrogen bond with water? And the answer, no. They aren't going to hydrogen bond with water, because in order to hydrogen bond with water, the hydrogen has to be bonded to what three elements?
Nitrogen, oxygen, or fluorine?
Nitrogen, oxygen, or fluorine. And chlorine's not it. If it was able to hydrogen bond, then what we might think is HCl might be miscible. Miscible means what? Yeah, infinitely soluble. But there is a limit to how much HCl you can cram in water, and that limit is huge. I mean, you can put a lot of HCl, but it's not infinite. You're going to max out. And you're going to max out, and that's what they call concentrated HCl. You know, what is that max? The max is like 12 molar, 12 moles of HCl in a liter, something like that. So if that's the concentrated stuff, then 6 molar is considered dilute, but 6 molar is also pretty concentrated. That's a lot of HCl in the water. So things play a role, you know, is the HCl pure, the gas? Is it HCl aqueous? You know, if it's HCl aqueous, is it 6 molar, 1 molar, 12 molar? You know, it makes a difference. You know, when I was in high school, like high school chem teacher always talked about drinking HCl. You know, he's going to drink HCl. But first he's going to mix some NaOH in. And then he's going to neutralize it to a salt, sodium chloride, and then drink it. As I was waiting all year for him to drink it, he never did. So I guess he didn't quite trust his chemical skills, maybe. I don't know. But then I thought about it, and we drink HCl every day. You know, do you know what the pH of tap water is? I don't know if you drink tap water, but if you drink tap water, do you know what the pH of this stuff is? Even our DI water, do you know what the pH of our DI water is? The pH of tap water is like pH 4, 4 to 5, which means it's acidic or basic?
Acidic.
It's acidic. And do you think there's chloride in tap water? Yes, so you're drinking HCl anyway, so it's not a big deal. It's just, what is the concentration of that HCl? It makes a huge difference. You know, if it's micromolar versus 1 molar, that's a huge difference, 6 orders of magnitude difference in concentration, 1 million times. Anyway, we'll be looking at that. If we look at dictionary definition number 2, the composition, structure, properties, and reactions of a substance. Similar, but the same thing goes here. I throw in chemical reactions as part of properties. Were you able to get these PowerPoints? Usually I don't use PowerPoints, but we'll do it for this. But tell me the chemical properties of HCl. I just copied the definition here. We just talked about that. We talked about physical properties and chemical properties. Chemical properties are just the reactions that it undergoes. So if we're thinking about the chemical properties of HCl, you know, what types of reactions does HCl undergo? Or, you know, what does it react with? Can you tell me everything HCl reacts with? Just give me a list. So, for example, does HCl react with platinum? Metal, platinum metal. Yes or no? Yes? Does HCl react with gold metal? Will HCl dissolve platinum and gold? We're going to be working with HCl a lot during the semester. So if you have any platinum or gold, better not bring it to the lab. Otherwise, you know, it's a gas. And the gas will start to attack your platinum and gold, wherever. You know, you can smell it as well. You know, even if you're working in the hood, your stuff could be exposed. So if you have any platinum or gold, should you worry? Well, you want to know, you know, certain properties, you know, for HCl. Like, for example, I was on the freeway, the 101 freeway, and there was a tanker truck that crashed. And there's billowing clouds of orange, yellow smoke coming off the truck. And I was one of the first cars there, so the news person was right in front of me, and I was listening to him talking, and he was saying, oh, there's a big HCl cloud behind me. I thought, that's not HCl. How could a billowing yellow-orange cloud be HCl? Do you know what it was? It was acid, yes. It was a strong acid, yes, but it was not HCl. You know what that acid was in the tanker truck? It wasn't sulfuric acid either. Sulfuric acid does sometimes have a choking odor to it. It was a colorless acid, but it decomposed. It reacted with something and was converted into a gas. Orange. Yep. It was nitric acid. Nitric. And the billowing orange was NO2 gas. NO gas usually comes off as colorless, then it's the oxidized air, NO2 gas. So it's nitric acid. But for HCl, let's think of the properties. Do you want to go through properties like this? Okay, after gold, what should I do? Silver? Does HCl react with silver? Does HCl react with copper? Does HCl, do you want to do it one by one like this? Not really. I don't want to do it one by one. And so what I want to do is I want to look at, you know, maybe simplifying things and grouping things into different categories. So when we think back to Chem 1A, how many different types of chemical reactions did you learn in Chem 1A? Okay, 3. How about you guys? Do you guys remember how many different types of chemical reactions? So for example, what would one type? One type of chemical reaction that's talked about in Chem 1A is the precipitation reaction. Okay, so that's one. Did you have any others that you recall? Acid-base neutralization. That's 2. Think of any others? Combination reaction. Remember? Combination decomposition reactions. That's 3. You remember any others?
Combustion.
Combustion. That's 4. Double replacement. 5. Single replacement. 6. Is that it? Actually, there are a whole bunch. There are a whole bunch, but what we're going to do is we're going to further simplify that because it's too many. And there's too much overlap in that. And so let's talk about that here. So we're going to focus our time on chemical properties. And so this is what chemists do. Chemists try to interrelate the composition, the structure, with the properties. And so we want to understand the properties. You want to understand the properties of HCl, you want to know what it's composed of. Well, it's composed of an H and a Cl. Actually, an H plus and a Cl minus, or well, this is covalent. There are different ways of thinking about it. Normally, when we think about HCl, you see a polar covalent bond here, and this would be in the gaseous state. But when water comes along and we dissolve this in water, then what happens here? It's very soluble in water, and when we dissolve it in water, what happens? It becomes ionized. That is, it gets pulled apart by the water molecules and creates the ion. So one of the ions is, okay, the H2O is going to pluck off the hydrogen, the proton we call it, on the HCl molecule. And that's going to leave chloride like this as an ion. So we have H3O plus and chloride. So that would be the composition. The composition might be molecules, like in the gaseous state, or it could be ions, like in the aqueous state. The structure, structurally, what do we do? For hydronium, we know the Lewis structure for hydronium. Looks like this. There's a positive. What do they call that charge here? A positive. What do we call that charge is called? The net charge we usually write with square brackets out like this and then put the net charge outside of that. But when I have a charge that's circled like that, that usually indicates what type of charge. Formal charge. We have different charges. We have the net charge, we have the formal charge, and we have two more charges. The formal charge, and then there's something called the starts with an O. Oxidation state is another charge. So the oxidation state of chlorine here is -1. The formal charge of chlorine is -1. So the formal charge and the oxidation state are the same for this. But over here, the formal charge on oxygen is +1, but the oxidation state is not +1. The oxidation state is actually, can somebody see what the oxidation state here is on oxygen is? Not -1, close. -2. The oxidation state is -2. Those are very useful. And so formal charge, oxidation state, net charge are useful to review from Chem 1A. We'll be looking at those because when we analyze things for properties, we want to be able to visualize. Chemistry, when we think about the chemistry, you guys recall, like, what's the most important force in chemistry? Is it like gravity? The nuclear force, the weak nuclear force or the strong nuclear force? It's electromagnetic forces, and primarily electrical forces. Electrical forces are the most important. If electrical forces are most important in chemistry, then we need to be able to visualize what's happening with the electron cloud, the electron density. And charges are critical for understanding that. And so when you show chemists, what's the formula for sodium? Well, it's like that. Or sodium ion. Sodium ion is totally different. Sodium ion is with Na plus. Whether you write a plus or a 0 here makes a huge difference with chemistry. And the same thing here. We want to know the total charge, that is the net charge, the formal charge, the oxidation states. We want to know what's going on with the electrons and electron cloud and how that's distributed. So how can oxygen have two charges? How can oxygen be a +1 here and a -2 there? So it's a +1 here with formal charge and a -2 here with oxidation state. Why is that? Oxygen doesn't have 2 charges, does it? Actually it has more, because there's one more, and that is the partial charge. Do you guys remember what partial charge is? Delta plus and delta minus? Partial charges. And so when we're thinking about structure, composition and structure, this is what we're thinking. This is what we're thinking in terms of, how is this going to behave chemically? And so we'll be going through this. But you probably want to just take a peek back at how do you do formal charges and how do you do oxidation states. Later on, we'll talk more about how to interpret those numbers, because that's what chemists are going to do. They're going to look at this, they're going to look at that, and they're going to try to surmise some properties based on that. And so the goal of chemistry is understanding the properties of matter based on composition and structure. Well, how do we do that? This is all this kind of Lewis theory stuff. Lewis structures, this kind of stuff. Lewis theory is based on, the general theory. What is the theory of chemistry? If you're thinking, well, first off, what is a theory? Do you guys know? Like, the scientific method? What are the steps in the scientific method that you've covered? Let's say. So this is just kind of a reviewing from Chem 1A, but since we're talking about theory, we should understand it in as much detail as possible. And so the scientific method, how would you describe it? This is typically what most scientists do. They come in, they do their scientific work, which is using the scientific method. This is the scientific method. The scientific method is how science evolved, basically. A lot of people propose many different things. And then through the scientific method, some things are filtered out. For example, the alchemists. The alchemists wanted to find the philosopher's stone. The philosopher's stone would turn like lead into gold. Was that based on the scientific method? No, and so people stopped looking. People stopped devoting all their time and money into it. Maybe not everybody. I'm sure there are people out there who are devoting their entire life savings and free time to it. So certain things get filtered out. This is how science is supposed to work. There's not one person who is who says what is right or what is wrong in terms of science. It's a collective thing where people work together to figure out. And so, what are the steps to the scientific method? And what exactly is a theory?
The first step is to make observations.
Yeah, typically we just make observations. And so those are just like factual observations. There's nothing to it. So for example, HCl is a gas. Pure HCl is a gas. It has no color. And so somebody observed that, and then, if you haven't seen it, then you can just learn from their factual observations. And this is kind of memorization part of it. Memorization. Some stuff is pretty useful to memorize. Some stuff is you can get by without memorizing. A lot of people memorize that HCl is a gas because it dictates how you handle it. HCl is such a common chemical. change the way we might handle it. Also color. And so just observations. But it's not just all observation. If we have to memorize everything, so if you want to know all the chemical properties of HCl, are you going to memorize all of them? And how many are there? You know, how many different chemical reactions can you have with HCl? Well, it reacts with so many different things. It'd be hard to compile a list of that, wouldn't it? And so, rather than observing, I mean, of course we can observe. We mix the HCl with platinum. Did it react? Did it not react? Okay, we go next, gold. We mix the HCl with gold. Did it react? Did it not react? But it's too much to do it observation by observation. And therefore we look for what? Patterns, yeah. We're going to look for patterns of... So rather than looking at individual, we look at like, okay, what are the patterns of reactivity for HCl? Maybe that's a little easier to deal with than one by one. It would be nice if these patterns are very consistent, reproducible, and the simplest pattern is a mathematical pattern. Although, you know, in terms of chemical reactions, maybe you can make a mathematical pattern out of that. But if we can get a mathematical pattern, then generally these patterns turn into... Colin, you got it? Mitchell? It's like a rule, but it's better than a rule. The scientists have a distinction: rules versus what? Law. Yeah. There's a big difference. Rules are, you know, there's plenty of rules. There are plenty of exceptions to rules. You know, we have a rule for this, a rule for that, but like solubility rules. You know, solubility rules are not laws. You know, there are going to be exceptions there, how you dictate or how you interpret those. And so if these patterns are really rigid, then we call them laws. Okay, laws are more reliable. However, not all laws are perfect. You know, some laws have withstood the test of time. Can you give me a law that... Like the ideal gas law. Ideal gas law, how reliable is that? Is that 100% reliable? 90% reliable? What would you say? You could use the ideal gas law in every scenario with 100% confidence? Or, well, it depends. Is the ideal gas law like written in stone and never violated, or are there violations of the ideal gas law? And what is an ideal gas versus a real gas? What's the difference between a real gas and an ideal gas? Well, that's stuff from... And so some laws are like that. The ideal gas law, yeah, there's a bunch of situations where it doesn't work. You know, we have to use the real gas law. One of the real gas laws, there's many, like for example the van der Waals equation, or the Virial equation, or one of these other ones. Some laws have withstood the test of time, like thermodynamics. You know, if you go on Amazon, there are lots of people trying to sell perpetual motion machines. You know, but the laws of thermodynamics says a perpetual motion machine can't exist. And so if that's correct, then the laws of thermodynamics are similar to the ideal gas law. There's some exceptions there. You know, there's some crafty developer on Amazon who made a perpetual motion machine. But people have been trying to find violations, because this way you can make energy. You can make energy from nothing, which would be great, because you could generate electricity at no cost. But those laws have withstood. So there is some variation in the reliability of laws. Laws of thermodynamics, people have been trying to find violations of that, but not successfully. Nobody's found a violation of the law of thermodynamics because there's going to be people who are going to debunk some of these perpetual motion machines. But the rules have lots of exceptions. Rules are in a totally different category way down here. Laws are much better, but sometimes they have to be modified. So for example, the law of conservation of matter, or law of conservation of mass, that's had to be modified. It's had to be modified because Einstein's relationship between mass and energy. Other laws have withstood. States. Okay, from a law, then all these are what we call empirical. Empirical just means by observation. We aren't really getting into the theory of things. And so if there's a law, for example, the law of conservation of matter, why is it? Why is matter conserved? That kind of thing. And so when people start to dig deeper, then they come up with a hypothesis. And then ultimately what we want is a theory. What a theory is a fundamental description of what's going on. You got all these observations, patterns, laws, whatever, but it's the fundamental description of what's going on. So if you understand it at a fundamental level, then you can make predictions. So if you understand the behavior of something, then you can predict that behavior. And so this is ultimately what we want. We want a theory, because with a theory, then we do not have to do empirical work. We don't have to get in the laboratory. We just predict what's going to happen. And so if we knew the theory, of HCl, then we can just predict everything. Will it react with platinum? Well, let me check the theory. The theory says no, it's not going to react. That's what we're going to do. And so what is that theory? What is the theory of chemical properties? This composition structure. What's the theory, the fundamental description of this relationship that we're trying to develop? Here. The theory underlying all of this. If we understood the theory, then we know how it's going to behave. We can just predict it. And so if we have the composition structure, then just make the predictions of the properties. Or if we have the properties, then we can predict what the composition structure must be. Well, a theory must do two things. A hypothesis is a tentative theory. So a hypothesis isn't as good as a theory. The theory has widespread acceptance. There are lots of hypotheses. Actually, some recent ones. So the recent ones that were in the news were there are two competing hypotheses about the origin of, let's say, COVID-19. One hypothesis was that it came from, a bat and through a market. The other hypothesis is it was an accident or potential accident, something like that. Those are hypotheses. And, there's not widespread agreement on one or the other. But eventually, when it gets to the theory, it should have widespread agreement. There should be a consensus for this. And so a theory is going to be a fundamental description of what happened, plus it's got to predict things. Why do we want? Well, we want to predict things so that stuff like this doesn't happen again. Why would you want to know the theory of the origin? We want to know the theory of the origin so to make predictions about preventing this kind of stuff in the future. So it's very important to know the theory, and so this is why people want to know the theory. They want to know the theory because they want to understand things at a more fundamental level. So it's this fundamental picture of what's going on. And two, we want to predict what's going to happen. And so we want to predict the properties of HCl. Well, tell me the properties of HCl. Well, one, do you know the theory? What is the theory of chemistry? Quantum mechanics. How good are you at quantum mechanics? Probably not great. Well, most people aren't, me included. And so I'm going to have trouble using quantum mechanics to predict it. And so what we're going to do is we're just going to look for patterns of reactivity. And that's fine. You know, we don't have to understand the theory of everything. It would be great if we did. And this is continually evolving. It's not so easy to apply the theory. And so these patterns we can get from observations. That's called empirical. Or these patterns we can get from theory. And this is what I call the two-pronged approach. The two-pronged approach is this. We want to use a mix of theory and descriptive chemistry. Descriptive chemistry is just observations to understand these patterns of reactivity. The more theory we understand, the less we have to memorize, which is always good. You know, the less we have to memorize, especially for people with limited memory like me. I have trouble memorizing things. All right, let's start it again. So normally when I, part of the theory is like, for example, Lewis theory or something, Lewis structures, that kind of stuff. But all that stuff is based on quantum mechanics. You know, it's a way that we can apply quantum mechanics. Really, there's just one underlying theory, and that is quantum mechanics. But from there, we get kinetic molecular theory, Lewis theory, valence bond theory, molecular orbital theory. Do you remember all those? And all those are just kind of specific applications of quantum mechanics to something. So when we look at Lewis theory, that's one of the things we can do is we can determine the formal charge like this, which formal charges I usually circle. And we can determine the oxidation states. Oxidation states I usually write in parentheses. You know, this is not a law. This is not even a rule. It's just a convention. Not everybody will follow convention. There have been plenty of people who disagree with this particular convention. But does somebody remember, because the more we understand theory, the less we have to memorize. So do you want to just memorize these oxidation states and formal charge? Do you want to memorize that for each? No, we don't want to memorize it. We want, although, there's a simple rule that we don't really have to understand the theory, But the more theory we understand, the more meaning we can get from these particular numbers. And so, I forgot to start the recording. Okay, recording was resumed, but let me back up a second. Yeah, so we don't want to have to memorize a whole bunch of individual observations. It'd be better to memorize patterns, but even then, we don't want to memorize patterns. It'd be better just to understand the theory. And so the more we understand theory, the less we have to rely on observations. And a lot of people say, memorization's useless. I don't think memorization's useless. I think memorization is very important. Memorization is very important because it helps you understand a lot of things. And eventually it leads to this. I mean, there are different ways we can approach, although this shows one direction. It goes both ways. So oftentimes we'll just use laws to predict them. We don't have to understand the underlying theory of the law. For example, did you ever ask yourself, where does the ideal gas law come from? PV equals nRT? Or did you just memorize PV equals nRT and use it? Well, most people just memorize and use it, but where did it come from, theoretically? Colin?
Didn't they make like a bunch of individual ones, like
Yeah, that's one of the ways it combined, but even the individual ones are just based on, observations. But is there some kind of theoretical foundation for that? And so that's it. Even the ideal gas law can be based on observations. But that's one way it came from. In other words, I'm asking, can you take quantum mechanics and derive the ideal gas law? That way you didn't have to take all those. Charles took all the observations, Boyle's, etc. And the answer is yes, you could do that. But going back to this, can somebody recall why these numbers are different like this? Like, for example, oxygen's +1 in formal charge, but -2 in oxidation state. Theoretically, what are we doing there? There's a trick we're doing. Do you recall that trick that we're doing? Colin?
For formal charges, you assume bonds are 100% covalent, so they share electrons. And then for oxidation state, you have to know electronegativity, and then assume that the winner takes all.
Yeah, and we call that type of bond where winner takes all. The opposite of sharing would be, or covalent. Ionic, yeah. And so when we analyze structures like this, we want to, composition structures. So when we're analyzing structures like this, then we can, because it's hard to visualize how the electron cloud is distributed in this. And so one of the things we do is we assume that the bonds or the electron clouds are 100% covalent, so they'll have a very even distribution. Or we assume that the bonds are 100% ionic, and that gives us our two extremes. The reality is it has to be somewhere in between those two extremes, and that's where partial curves come in. And so when we look at this bond, it's not 100% covalent, correct? Because chlorine's more electronegative. It's not 100, so it's going to pull more of the electron cloud towards it, and less electron cloud towards hydrogen. But it's not 100% ionic. It's somewhere in between. And so that's what we call partial. So chlorine we label partially negative, hydrogen we label partially positive. And so we have the delta plus and the delta minus. If we look at the formal charges are 0. But the actual charge isn't 0. And so formal charge is not accurate. This is not 100% covalent. If we assume the bond is 100% ionic, then what's the charge on chlorine if it's 100% ionic? -1, and the charge on hydrogen would be +1. And it's not 100% ionic. It's somewhere in between 100% ionic and 100% covalent. But what is that in between? What's the number there? We want to be quantitative. And so being quantitative is difficult unless you adept at quantum mechanical calculations. Well, nobody's really that adept, so what we use is we use a computer to calculate things. But in the meantime, what we're going to do is we're going to analyze things in terms of formal charge, oxidation state, and then think, is it somewhere in between? And then we have an idea of how the electron cloud is distributed and the charges. Because chemistry is this interaction of the charges, the interaction of the electrical charges. This is what makes hydrogen bonding. What makes hydrogen bonding hydrogen bonding? Hydrogen bonding is hydrogen bonding because an unusually large dipole, which is created from an extremely high electronegativity of oxygen, nitrogen, and fluorine, and it makes almost a full positive charge on the hydrogen. And so that type of stuff, the more theoretical understanding we have of hydrogen bonding, polar interactions, chemical reactivity, this kind of stuff, the better. And then when we dissolve in water, we form full ions. And so this is why the oxidation state and the charge are the same for chlorine. However, it's a little different for hydronium because it's not monatomic, it's polyatomic. And so we want to understand the theory as much as possible, but it can be too much. We'll do little bits here and here. And so this is why I say review formal charge and oxidation state, because the more we understand that, the more we can understand and apply theory to this, at least Lewis theory. But for the most part, we're just going to be looking for patterns, patterns of reactivity. And these patterns aren't laws. They're just patterns that are going to be useful for predicting chemical reactions. And so let's take a look at the patterns. And as far as patterns of reactivity goes, I don't break it down into like 7, 8, 9 different patterns. I break it down into 3 patterns of chemical reactivity. In Chem 1A and Chem 4 we discussed this, but if you had Chem 1A and Chem 4, you might have, in Chem 4 I'm supposed to have you guys memorize 7 different patterns of reactivity, but it's too much. Again, they're inconsistent. So we can go different ways. So for example, if we knew the properties
we can get some insight into the composition and structure. So let's say this has an extremely high melting point. If it has an extremely high melting point, then that gives you a little bit insight into the structure. The structure must consist of very strong bonds. You know, high melting point, strong bond. Probably a covalent lattice or maybe an ionic lattice. You know, those types of things we can get. Or we can go from composition and structure to properties. And so we use this all the time. We use properties. So for example, if I have a liquid here, and I look at it, and I'm really thirsty, would you drink this liquid? It's probably water. But how can you tell it's water? You know, let's say there was an earthquake and this is all I could drink. Would you trust it? Well, maybe not, because some people put HCl in these. If you're a geology major, which I was, I went to, I forgot to mention this, but I started at Santa Barbara City College as a geology major. And geology majors, we had a little belt, and in the belt we had a little hook thing for our HCl squirt bottle, which is exactly like this, and we filled it with HCl. And then when you're out in the field, you can start spraying rocks and minerals with the HCl. And one of the chemical properties of HCl is HCl loves to react with carbonate containing rocks and minerals, and they just start to effervesce, fizz. So that's one of the things we look for. But now, are you going to drink this? How do you know what its composition is? How can you tell what its composition is? Is it pure water? Well, we look at the properties. If this stuff boiled at 88 degrees Celsius, would you be drinking it? No. If it boiled at 112? No. If it smelled funny? No. We're going to compare its properties, and eventually, after you compare enough properties, then you might be convinced. You still might not be convinced, because this could have trace contaminants, you know, like lead, methyl mercury, something like that. But we're going to analyze the properties, and sometimes analyzing a property is very difficult because of that. And so sometimes we just end up separating this. You know, just in other words, I'll drink it after I distill it. You know, it's like that. Most of the time, we're going to go the other way. You know, this is using properties to determine composition is very frequently done. This is called characterization. Let's say you made something in the laboratory. You made something, but the next step is you need to characterize it. Characterize is determine what the heck you made. You know, what is it really? And so this is used often to ID unknown substances. It's unknown substance, but if somebody else has studied it and written a list of its properties, then we can make a comparison. If it's a new substance, then you know, what we want to do is figure out the composition, you know, how much carbon, how much hydrogen, etc. That's called elemental analysis. Okay, this is the question that I had, and that's going the other direction. Going the other direction, we're going to use the composition and structure to determine the properties. So I know the composition, hydrogen, chlorine. I know the structure, those are the structures. So what are the properties? So does HCl undergo combination reaction? Does it undergo decomposition? Does it undergo acid-base, single replacement, double replacement, combustion, precipitation, etc.? Okay, what we're going to do is we're going to just not even deal with this scheme here. I have problems with that list in particular. So if you're trying to recognize a pattern, what pattern is this? So if I take HCl and HNO3 and react it with gold, what is this? Does that fit any of the patterns I just listed there? No, and so you need another pattern. And so this is a question mark. This is a third pattern. I mean, not a third pattern. Maybe this is a triple replacement, something. I don't know. We're going to have to keep adding. I don't want to do that. And so we need something else. It's not a comprehensive list. So what I want to give you is a more comprehensive list. And it's confusing. So for example, this first reaction here is a combination reaction. And the second reaction here is a combination reaction. But they're totally different. When I look at these two reactions, these have totally different what I call driving forces to them. Driving forces is what drives the reactions to occur. In other words, nature tends to try to minimize energy. So we try to go from higher energy to lower energy, and this is the hood. A very tight window cell. And then there's one other thing that we look for, and that's entropy. Nature tends to maximize entropy. You've heard of entropy before? What is entropy? Entropy is a measure of order. Things tend to become disordered. Like this room tends to become a mess versus it doesn't really tend to become more ordered. In other words, there's a tendency towards things becoming disordered versus ordered. That's entropy. We'll talk more about those in chapter 13. But these two are quite a bit different. And just because you memorize this particular pattern, can you see that same pattern here, or is that a totally different pattern? And both of these are called combination reactions. So you understand this combination reaction. Does that automatically, could you have predicted this combination reaction? No, because they're totally different reactions. And so this is my argument for not bothering memorizing this. Oops. Don't bother memorizing this. It's a waste of time. Instead, I'd like you to memorize this. We're going to have three basic types of reactions. Each type of reaction is going to be dictated by a particular driving force. So they're all going to look similar in certain ways. Metathesis looks like other metathesis reaction. Acid-base looks like other acid-base, and oxidation reduction looks like other oxidation reduction in a broader sense. There are others that, like photochemical radicals, but they're all kind of fundamentally the same. And so I'd like to break it down into three fundamental types of chemical reactions. What do I call them? The first one's metathesis, which we're going to look at today. And but you've seen it before. This is not a metathesis reaction here. If I looked at the first two, I might say it's a metathesis, because metathesis reactions are, one type of metathesis reaction is a double replacement reaction. And so if I look at the first two, this could classify as a double replacement. Double replacement pattern has an AB plus CD. Do you guys remember that? AB plus CD. If I look at the last two, what type of pattern does that look like? It looks like a single replacement. AB plus, or something, AX plus B type pattern. Or the first and the last. This is a very famous reaction. HCl alone does not react with gold. So I asked you, does it dissolve gold? HCl will not dissolve gold. HNO3. HNO3 is what acid again? You guys remember the name of this acid? Nitric acid. Nitric acid alone does not react with gold, but a combination of HCl and nitric will dissolve gold. And this combination of HCl and nitric is called aqua regia. Aqua regia is royal water, and this will actually dissolve the gold and get it to dissolve. So you don't want to have any gold near aqua regia for dissolving. How does it work? And what types? There's two types of reactions that are happening. One is the oxidation reduction, but it doesn't have enough driving force. But in combination with the HCl, which is going to make an acid-base type reaction, then it does have enough driving force to get this to go. Look at that. The reason why these two reactions don't agree is the first one is what type of reaction? The first one is a combustion type reaction here, or an oxidation reduction reaction. And so the first one is redox, we call it. The second one is not a redox reaction. The second one is what we call Lewis acid-base reaction. And so that's why they didn't look right. And so, and that's why I wouldn't categorize both of those as the same type of reaction. So in terms of these three types of reactions will have three types of driving force. The driving force here is the formation of more thermodynamically stable products from less stable reactants. So we're going from higher energies to lower energies. That's what's driving. It's downhill type process. In terms of descriptive chemistry, what we want to go is from more reactive substances to less reactive substances. So this is why, for example, precipitation. Precipitation, you form a solid crystal precipitate, which is stable, typically. And so precipitation works well. Or neutralization, we're neutralizing strong acids and strong bases and making weaker acids and weaker bases from them. And so in terms of descriptive, those are the types of things we look for in going from this to that. In terms of redox, we look for going from more powerful oxidizers and more powerful reducers to weaker oxidizers, weaker reducers. And so for these three types of reactions, we're going to be focusing on three different driving forces. There's some overlap, but for the most part, they're different. So when I ask for chemical properties, what are the chemical properties of HCl? Then I'm asking for three things. What are the metathesis properties of HCl? What are the acid-base properties of HCl? And what are the redox properties of HCl? And so once I answer those three things, then I have all the chemical properties of HCl that I want. So, the three basic categories, metathesis, acid-base, redox, but there are sub-categories here. So for example, in metathesis, one of the biggest ones are double replacement. But not everything fits a double replacement pattern. There are lots of things that don't fit a double replacement pattern. So one of the things that wouldn't fit a double replacement pattern is this, like for example, chloride. Chloride loves silver ions. When chloride and silver ions meet, they precipitate a silver chloride solid. Is that a double replacement reaction? No, but this is what we call metathesis. Or I could have sodium chloride reacting with silver nitrate. When sodium chloride reacts with silver nitrate, then we produce silver chloride precipitate plus sodium nitrate. Is this a double replacement reaction? Yes, this is a double replacement reaction, but both of these are metathesis reactions. And so the first one I call an ion combination. Chloride ions like to combine with silver ions. The second one is double replacement. Both of them are the same reaction. For acid-base, we have 3 types of acid-base reaction depending on the definition of an acid and base. We have 3 definitions of what an acid is and what a base is. Starting with the most limiting, Arrhenius. Arrhenius acid, what is that? Well, it's H+. Arrhenius base, OH-. But that's not enough. What about ammonia? Ammonia is a base. And therefore we have the Bronsted-Lowry. Bronsted-Lowry takes care of ammonia. Ammonia is a proton acceptor. That's a base. But that's not enough. So for example, CO2. One of the chemical properties of CO2 is it's an acid. If you, if you hyperventilate, it changes your blood pH. And that is, it's dealing with the CO2 and the balance of CO2 with your blood. And so anyway, we have the final definition, which is Lewis. Lewis, acids and bases, this is most comprehensive. We only need one definition. But doing Lewis acid-base reactions and predicting the products of Lewis acid-base reactions are a bit more complicated. Bronsted-Lowry are by far the easiest to predict. The acid is a proton donor, the base is a proton acceptor. The only problem is not everything fits Bronsted-Lowry. So for example, if we look at this previous reaction, can you tell that this was a Lewis acid-base reaction? Is that easy to see? Do you see what the Lewis acid is? Lewis acid is CO2. You know what the Lewis base was? Oxide in calcium oxide. And so I had a Lewis acid-base reaction between the CO2 and the oxide, which made the calcium carbonate. Well, so it's more difficult to predict. Bronsted is a lot easier because you have a proton. The proton gets transferred from the acid to the base. So a lot easier. And so when we study acid-base reactions, we mainly look at Bronsted-Lowry and then Lewis. Lewis being more difficult. So I didn't spend much time in 1A looking at Lewis acid-base reactions. For redox, the most common redox that you've encountered probably are the single replacement. Those are redox. Double replacement are not redox. They're a totally different driving force. So in double replacement, we look for precipitation, we look for gas formation, we look for stronger acid and weaker acid. But in single replacement, if we have precipitation, it makes no difference. In single replacement, we look for something entirely different. We look at the activity series, and we look at going from more active element to less active element, etc. And so the single replacement, you've also done something called skeleton redox. This is in chapter 5, at the end of chapter 5, where you balance out the oxygens by adding water, and then you balance out the hydrogens by adding H+, etc. And then I discussed something called the redox chart method, which is a more general method. All right, we're going to have some basic assumptions here for predicting reactions. Our concentrations are going to be what we call standard thermodynamic concentration. Have you ever heard of standard thermodynamic conditions? So for example, what's the difference between a delta H and a delta H naught? Delta H versus delta H naught. Can somebody remind me what the difference is?
The knot is at standard conditions.
Yeah, at standard conditions. So what is the standard conditions for thermo?
1 ATM and
Okay, 1 ATM or 1 bar for gases. Okay, that's correct.
I don't remember the rest.
You don't remember the rest? Okay. Anybody else remember the rest? Okay, let me tell you one other one. Concentrations, 1 molar. So this is standard thermodynamic concentration, 1 molar, 1 atmosphere. What about temperature? Is there a standard thermodynamic temperature? And the answer is there's no standard thermodynamic temperature. However, what's the most common temperature that we run reactions at? The most common temperature that we run reactions at is at 0 degrees Celsius, 273 Kelvin, or is it 25 degrees Celsius, 298 Kelvin, which we call room temperature.
273 Kelvin.
273 Kelvin, 0 degrees Celsius. Yeah, that could be our standard temperature. That's the standard temperature for gases. So it would be good if the standard temperature for gases and the standard thermodynamic temperature were the same, but they aren't. They aren't the same. And the reason they aren't the same is because at 0 degrees Celsius, water will freeze. And although most of the time we're working with solutions, so there's boiling point depression, from chapter 14. So it still might be a liquid, but we're getting close to the freezing point of solution. So we've got to be careful. So there's no standard thermodynamic temperature, just the most common temperature that we use and most of the data that we're going to have is at 298 Kelvin. But we don't call it standard temperature. So the first thing is I want to set the conditions to standard thermodynamic or close to it. It doesn't have to be perfect, just close to it. Reason is because extremely low or extremely high concentrations may require compensating for thermodynamically. So I could drink HCl as long as it's like micromolar concentration or something, right? I could drink it without having to worry about it. In fact, your stomach has more. So under thermodynamic conditions, if I take HCl and silver nitrate, it's going to precipitate out silver chloride, like I have over there. I'm going to get HNO3. But under very dilute conditions, let's say I tried to precipitate it using tap water, it may or may not precipitate. It depends on the concentration. And so under very dilute conditions, I don't predict the same thing. I might see no reaction here. Because in order to see it precipitate, I need like a milligram of it or half a milligram to visually see it. I might not see any precipitation. Under standard thermodynamic conditions here, I get no reaction here. Silver chloride plus HNO3, no reaction. But if I use hot concentrated nitric is closer to 16 molar. And so hot concentrated nitric is going to be much more reactive. And when I do this, I get a reaction. In fact, I'll get plumes of orange smoke. There's a redox reaction happening. And the hot concentrated nitric acid is oxidizing my chloride to form chlorine gas and NO2 gas. It's a nasty mixture of gases. You should do this in the hood for sure. With lead-2 nitrate is a bit tricky because with a stoichiometric amount of sodium hydroxide, we get a nice white precipitate. But if I add just a slight excess of sodium hydroxide, you think I wouldn't have any problem. But what happens is that precipitate dissolves. And I form this. This is called a complex ion. The name of this complex ion is trihydroxoplumbate 2 ion. We'll learn how to name these in chapter 24. And so this precipitate actually dissolves. Normally when we try to precipitate, we add excess precipitating agent. We add excess precipitating agent to maximize the amount of precipitation we have. But you wouldn't want to do that in this case because of this. So we have the thermodynamic driving force. The thermodynamic driving force is to properly predict reactions. This is a limitation because when we do this, we're looking at thermodynamic driving forces. There are two things we need to look at when we're dealing with chemical reactions. One, we need to know the thermodynamics of it, the energetics of it. Two, we need to know the kinetics of it. Just because we have a driving force thermodynamically doesn't tell us the reaction is going to happen. We need to know the kinetics because sometimes it's very slow. So even though there's a driving force, it's extremely slow. And that's because of something called activation energy, which we'll talk about when we get to chapter 20, I think, or 19. No, 20. When we look at this, so for example, do you guys have the 11th edition or the 10th edition of Petrucci? You know? It depends on the edition. If you have the 11th edition, then we're fine. If you have the 10th edition, then kinetics used to be chapter 14, I think. And so you'll have to modify the sequence here. 13 or 14, I can't remember. The chapters are pretty much the same. They just switch the order. So we need to know the kinetics. So which one is more stable, diamond or graphite? Both of these are pure carbon. So do they both have the same energy? When we talk about energy, I'm talking about, well, there are two types of energy, broadly. What are they? Kinetic energy and potential energy. So let's say both of these have the same kinetic energy. In other words, they're both at the same temperature. So if I have room temperature diamond and room temperature graphite, the kinetic energy is the same. However, the potential energy is different. The potential energy is going to depend on the structure. You know, diamond has sp3 carbons in the lattice, tetrahedral. Graphite has sp2 carbons. It would be trigonal planar. It forms hexagonal rings. So which one of those is more stable in terms of potential energy? You know? And it turns out that graphite is slightly more stable than diamond. And so graphite's more thermodynamically stable. If graphite's more thermodynamically stable and diamond is less thermodynamically stable, then diamond's higher in energy. If diamond's higher in energy, then nature tends to want to minimize energy. And so what should happen is that the diamond should decompose into graphite. And so that's a thermodynamic driving force. There's a thermodynamic driving force for diamond decomposing into graphite, but is it going to happen? No, it's not going to happen because what we say is that it's metastable. In other words, diamond is kinetically stabilized. That is, it's too slow to react. It's too difficult to get it to react. In order for diamond to react, we have to break all those sp3 bonds and reform sp2 bonds. Do you guys remember sp3 hybridization, sp2? Stuff? Okay. And so kinetically, that's very difficult to do. That's a big hoop to shoot through, or a big hill to climb. It's tough. And so what it has to do is it has to go uphill in order to go downhill. And that uphill part is a bit too big to make it downhill. And so that's what we're looking at kinetics. So in order to properly predict reactions, we need to look at them both from a thermodynamic perspective and a kinetic perspective. But first off, we're just going to focus on the thermodynamics. In fact, all the equilibrium chapter stuff I talked about earlier is going to be all thermodynamics. All right, so let's take a look at metathesis reactions first, which are typical double replacement reactions. They might have a different pattern, like the ion combination. But it's either going to be ion combination or double replacement. So for example, on a test, I think it was Chem 4, I can't remember. Maybe it was Chem 1A. I gave something like this: sodium chloride plus potassium nitrate plus silver nitrate yields what? And a lot of people left it blank. They couldn't figure it out because it didn't fit any of their pattern. But in this case, I mean, there are different things you could do. You could treat this as, you know, a double replacement here, a double replacement here, a double replacement here, so we have 3 combinations of double replacement. Or we could break this out into what I call the inventory. We just inventory the ions and see what ions like each other. And we already know chloride ions like silver ions. So very simply, this just makes silver chloride precipitate. And so it might not fit the double replacement pattern. Therefore, I don't call them double replacement. We call them metathesis reactions. Metathesis are just switching partners and seeing which partners attract and combine. That's it. And we try all combinations to see if it leads to what I call a favorable ion combination. So the goal of metathesis is just to find a favorable ion combination. What are favorable ion combinations? Ion combinations that result in a precipitate, ion combinations that result in gas formers, ion combinations that result in going from a stronger acid to weaker acid. Those are the driving force for all metathesis reactions. Okay, it gets a little bit more complicated because weak electrolytes, are not ions. Weak electrolytes are mostly molecules and a small amount of ions. And so a molecular compound like ammonia is for the most part ammonia molecules. But it's a weak electrolyte, and weak electrolytes partially ionize or partially hydrolyze in water. And so ammonia, what happens with ammonia is it weakly hydrolyzes water. That is, it reacts with water to break it apart to form ammonium ions and hydroxide ions. Since it's weak, this is favored in the reverse direction, and so it's mainly ammonia and water. But there are small amounts of ion. These small amounts of ions can react in metathesis. So it doesn't have to be ion combinations. If we have a weak electrolyte, then those weak electrolytes will form ions, and those ions can react. And so we have to be careful here. And so if I did something like this, I did ammonia plus silver nitrate. And I go, that doesn't look like a metathesis because ammonia is not an ion, but it's a weak electrolyte. It's a weak base. And therefore, this could potentially be a metathesis reaction. And in fact, it is. It's going to form silver hydroxide. That's what you'd predict initially, silver hydroxide. So what do you know about precipitates? So precipitates are going to be insoluble solids. There are different solubility rules. I posted some solubility rules from our book on Canvas. And I'll give you another set, which are easy to remember, easy to memorize, that we used to teach here in Chem 4. And there are 7. And so let's quickly go through those here. 1, group 1 and ammonium compounds are all. So if you have ammonium or group 1 would be sodium, potassium, lithium. In a compound, they're all soluble. Soluble. 2. Do you guys still have it memorized, or? Colin, you have it memorized still? Mitchell? Rafan? Some of them? Yeah. If you need to memorize things, and my memory is bad too, I'll forget it easily. I didn't do much this summer, so I just forget things. But if you need to memorize, then you have to do maintenance. And so I listened to this guy who has a world record in memory. And the maintenance intervals, like, they're more frequent initially and then become less frequent. So if you need to have it memorized, then you should refresh your memory like once a month. And then eventually it turns into like 3 times or 4 times a year, and then once a year. And then you'll always have it memorized, if it's important. It's important for certain things, like, let's say you want to go to medical school or something like that. And so you got to take all these requirements, and then you have to take the MCAT. And by the time you get to the MCAT, do you remember any of this stuff? If you have a really great memory, like a photographic memory, yes. probably. But if you don't, if you have a normal memory, then maybe you forgot everything. If you forgot everything, how much time do you have to go back and review it all? And so this is why a lot of people take these gap years. They'll take a gap year to review all of chemistry because they forgot it all. Or gap years. I've had. And so once in a while you go through this. This is why I keep notes. I keep notes around for classes and just flip through them if I need to refresh my memory. Okay, after group 1 ammonium compounds, then we start looking at anions. And the first set of anions that we look at are NO3 minus, which is called nitrate, CHCOO minus. Do you know what we call that? CH3COO minus. You recognize that one? Acetate. Acetate's commonly written like this, or C2H3O2 minus. Acetate. Nitrates, acetates, and chlorates. Do you remember the formula for chlorate? ClO3 charge minus. Good. Good memory. Nitrates, acetates, and chlorates are all soluble. Now, remember, is this a law or a rule? This is a rule. There are exceptions here. So, for example, mercury acetate, mercury 1 acetate is insoluble. But, you know, rules are, there's gray areas, it's close enough, we'll say. You know. Same thing with the group 1, like sodium uranyl acetate. Sodium uranyl acetate is a sodium salt, but it's insoluble. And so just a rule. There are going to be exceptions. Okay, after nitrates, acetates, and chlorates, we look at, or we look for chlorides, bromides, and iodides. Chlorides, bromides, and iodides are all soluble, except which ones? Yeah, silver, lead, and mercury. Which would be silver plus. Silver only has 1 charge. Lead has 2 charges, plus 2 and plus 4. Just lead 2. Lead 4 is actually soluble. So lead 4 chloride, soluble. Lead 2 chloride, insoluble. Bromides and iodides, the same. And this, what is this called? Hg2, 2 plus. Mercury 1. Mercury 1 and mercury 2. Mercury 2 chloride is actually soluble. It's more molecular, we say. Less ionic. 4. We look at sulfates. You guys remember the formula for sulfate?
SO4
And charge?
minus?
Close.
2 minus?
2 minus. SO4 2 minus. Sulfate. Sulfates are all soluble, except now what do I mean by soluble? There are 2 definitions of solubility. The first definition is qualitative. You know, will it dissolve in water or won't it? The second definition is quantitative. If it dissolves in water, exactly how much dissolves? And this is quantitative. For us, it's qualitative. So what we consider soluble is greater than 0.1 molar. If it's less than 0.1 molar, the solubility, then we call it insoluble. This is a very gray cutoff. Insoluble means it's less than 0.1 molar. And slightly soluble, you know what slightly soluble? Slightly soluble is about 0.1. And so here, These are all soluble except for silver. Silver, I'm going to put a little asterisk here because silver is borderline. Silver is in the slightly soluble category here. So it may dissolve, it may not dissolve, depending on the concentration, how much you got. If you just have a tiny bit, it'll dissolve. But if you have a lot, you aren't going to be able to dissolve all of it. Silver, lead, 2, mercury, 1, mercury 2, calcium, strontium, and barium. So a few more exceptions here. So sulfates are all soluble except for things like lead 2 sulfate. Won't be. They'll be insoluble. What about iron 3 sulfate? Iron 3 sulfate would be soluble. It's not one of the exceptions. All right, that's number 4. Let's go on to number 5. Let me write it here on the light. Number 5 is the mostly insoluble species. And the first one we're going to look at is S2 minus. S2 minus is called sulfide. And sulfides are mostly insoluble. So sulfides are insoluble except do you recall the exceptions for sulfide? Group 1, ammonium, and yeah, except it's magnesium's in there too. So we'll call it group 2. So the weird thing here is calcium, strontium, barium, but magnesium's missing. And the reason magnesium is missing is because magnesium sulfate is actually soluble, whereas calcium sulfate is insoluble. And up here, chlorides, bromides, and iodides, where's fluoride? Fluoride's missing. Well, fluoride has too many exceptions. So if you need to find fluoride, it's best to look in the book, to see if it's soluble or not. But here, I call this group 2 rather than calcium, strontium, barium because now I can include magnesium in there. 6. Hydroxides are insoluble, except, I don't know, did I do this in the right order? Maybe not. 5 and 6 you can switch the order, or whatever makes it easier. These are insoluble except for group 1, ammonium, and calcium, strontium, and barium. So calcium hydroxide is soluble. It's not the greatest solubility. It's greater than 0.1, but it's not much greater. And so if you had a bunch of calcium hydroxide, most of it won't dissolve, but enough will dissolve to call it soluble. So you might switch these to make it a pattern. When you're trying to memorize things, you might say, like for example, sulfates end with calcium, strontium, barium, and then hydroxides end with calcium, strontium, barium. In fact, I think I screwed it up. I think this is 5, that's 6, but it doesn't really matter. The only one that matters is number 1. If you do number 1 first, then that'll save you having to look at all the anions, if it's a group 1 or ammonium. All right, 7, phosphate. What's the formula for phosphate? CO4 3 minus. Carbonate, CO3 2 minus. Chromate, CrO4 2 minus. Good.
These are all insoluble, except group 1 and ammonium. And so usually you look at rule 1 first and then any of the others in any sequence. It doesn't have to go in numerical order. So if we form a precipitate, that's a good thermodynamic driving force. You know? And so like this earlier reaction here, I expect this reaction to occur. We're forming this precipitate of silver chloride. And that would be the driving force. Yeah. But that's not the only thing. Let's say there's no precipitate that forms. If there's no precipitate that forms, then we look for other things that might indicate thermodynamic driving force. And one of those would be stronger acid to weaker acid. And then typically what we do here is we just consult the Bronsted chart like this. Chart of Bronsted acids. A lot of people have the 7 common strong acids memorized. What are the 7 common strong acids? HClO4, perchloric, HI, hydroiodic, HBr, hydrobromic, HCl, hydrochloric, HClO3, chloric acid, H2SO4, sulfuric, and HNO3, nitric. So these are the 7 common strong acids. The rest are weak. But what we're looking for is we're looking to go from a stronger acid to weaker acid. We have to be careful because, you know, the strongest acid shown here is HClO4. But it turns out, and the weakest of the strong acids is HNO3, but these are equal in strength in water. All the strong acids have the same strength in water because all strong acids are strong electrolytes. Strong electrolytes ionize 100%. And if these ionize 100%, then they're going to ionize 100% into H plus and the anion. And so all of them are going to yield the same, whereas these partially ionize. These partially ionize the weak acids, and therefore we don't generate the same amount of H plus. Since we generate the same amount of H plus with the strong acids, we call that the leveling effect. Have you heard of the leveling effect before? The leveling effect states that all strong acids have the same strength in water. In the gas phase, they don't. That's why HClO4 is at the top. But in water, these are plenty strong enough to ionize 100%. And so the leveling effect. We also have a leveling effect of strong bases. We'll talk about the leveling effect some more. We'll go along. And so you should just review something about strong, weak, and non-electrolytes. Strong, completely ionized. This would be strong. Weak, partially ionized. And non, don't ionize at all. All right, what if we aren't going from stronger acid to weaker acid? What else do we look for? We look for gas formation. All we need is one driving force. We don't need all 3. The 3 driving forces are precipitation, stronger acid to weaker acid, or gas formation. Gas formation, if we form an ion combination of hydrogen ions and carbonate, that's carbonic acid. Carbonic acid decomposes. Do you know what carbonic acid decomposes into? Water and carbon dioxide. So gas formation, CO2. This is why geologists carry bottle of acid. They carry bottle of acid to combine H plus with carbonate. H plus with carbonate makes carbonic acid, and then it starts to bubble. And so carbonic acid doesn't last. It's very unstable. And so people put quote marks around it because it immediately decomposes into H2O, liquid, and CO2 gas. H2SO3, how do you name that? Is H2SO3 sulfuric acid? No, H2SO3 we call sulfurous acid. Sulfurous acid decomposes into H2O liquid, and sulfur dioxide gas. Sulfur dioxide is quite poisonous. Ammonium hydroxide is unstable. So if we have ammonium combining with hydroxide ions, that decomposes into ammonia, aqueous ammonia, and H2O liquid. We don't want to mix sulfide with hydrogen ions. Sulfide with hydrogen ions produces the very toxic hydrogen sulfide. It's a gas. We don't want to mix hydrogen ions with cyanide ions. That produces hydrogen cyanide, which is a very toxic gas. Etc. So we look for ion combinations that might produce gas. Like these. All right, so why don't you try this metathesis reaction here? Calcium carbonate and sulfuric acid. So go ahead and work on this one. You could work. So the precipitation is very tricky for calcium sulfate because it depends on which one ultimately is less soluble. So we'd have to look that up because it's not something that's easy to see directly. So if calcium sulfate's less soluble, it's more stable, reaction should go forward. If calcium carbonate's more or less soluble, then that's more stable and it shouldn't react. That kind of stuff. So we have to take a look at the solubility. Now looking at the solubility is easy. I typically look at Wikipedia, but it's something you can't really do on tests. You can look for other things that give you indications, like structure. You know, if we know something about the structure, then we can deduce certain things about the properties. And so let's just do. Change So this is the quantitative solubility. Quantitative solubility is how much dissolved. So keep this in mind. Solubility 0.26 grams is for the dihydrate. So 0.26 grams for calcium sulfate dihydrate. For calcium carbonate, solubility is 0.013 grams. But this is grams per liter. Was the other one grams per liter? Let's take a look. No. This is grams per 100 milliliters. So I'm going to have to multiply by 10. If I multiply by 10, that's 2.6 grams per liter. So 2.6 grams per liter for calcium sulfate. Calcium carbonate, 0.013 grams per liter. Which one's more soluble? Calcium sulfate is a heck of a lot more soluble than calcium carbonate. So does it make sense to precipitate out calcium sulfate or calcium carbonate? Which one's less soluble? More stable? Calcium carbonate. So you can't use precipitation as a driving force. Precipitation does not work here because calcium carbonate is a less soluble solid. Calcium carbonate's the favorable precipitate. It's calcium carbonate versus calcium sulfate. Which precipitate wins? Calcium carbonate wins. But all we need is one driving force, so look for another driving force.
There are actually two more driving forces for this one. And so two out of three is pretty good. Lewis acid. So you're going to have to get more familiar with Lewis acids. Now, Lewis acid is more complicated than Bronsted. Bronsted acid is a lot simpler. We're going to be dealing with a lot more Lewis acids in Chem 1B.